Welcome to your first video of my Earth Science class. Now I know that obviously we'd rather just be in class and then make it, well, maybe we'd rather be in class. I would rather be in class because it's a lot easier for me, and I think you probably would too, whether you admit it to me or not. But don't worry about it. We're not gonna talk about that now. What we are gonna talk about is astronomy. Now this is our first unit that actually deals with Earth science stuff, and we can talk about it all we want, and we can discuss why we have to learn Earth science, and we will. Don't worry, we'll get to Earth science. But what we're gonna do right now is just, if we want to learn, we got to start from the beginning of it. And where else to go than with the formation of the universe. Now, I know this is kind of, people have their own discussions, whether it's, if you want to get into the religious side or the political side. And I'm going to tell you right now, on day one of these kind of notes, that I'm not here to discuss that stuff with you. You're allowed to, and I want you to have your own thoughts, obviously, both religiously and politically and whatever else. You have yours, I have mine. Mine are not going to influence how I teach you, so don't worry about that, okay? I'm not going to bring it up. I'm not going to try to force what I think onto you. Here's what we're going to do. We're going to learn science, and that's it, the end. I'm going to teach you science. Whatever you do with it is what you want to do with it, but that's what we're going to go. All right, so back to this. How the universe began. Well, it starts off with the Big Bang Theory. Now, obviously, this is a TV show, and yes, some people tell me I look like and act like Sheldon, and that's whatever, but, I guess I'll take the compliment. I just wish I had the money that he had, but I don't. But what I do have is a certain set of skills that can teach you Earth science, and we got to start from the beginning. Every unit is going to start from the beginning and build a framework, and then we'll build off that to get more and more complex as we go towards the test. Your favorite thing. So this is going to start with the thing called the singularity. Now the singularity was literally what it sounds like. It's a single point of space nearly 14 billion years ago. Billion with a B. And we're going to talk about how long ago that was in class to kind of put it into perspective. But just know that's a really long time ago. And the singularity is something we define as the point that all energy and all universe and all space started from. Now, this is going to expand during a time of what we call inflation. Now, we can talk about inflation if you have specific physics questions about that, and I know some of you might have some physics questions about that. We can get into it, but for right now, let's just run with it. Before we do anything else, what we have to form are stars. So we have our first set of stars. Now these don't have anything around them. There's no planets, there's no other smaller kind of stars orbiting them, there's no binary systems. What we have is just basic first stars. Only hydrogen, helium, beryllium, and lithium are going to be available here. And if you look at the periodic table in the back of our room, they're the first 4 elements. We don't get planets till billions of years later. Some of these stars have already died, and we call that a supernova. And a supernova is when basically the star can't handle itself and it collapses and it explodes. And eventually, you get some that happen the right way, we get what we call black holes. That's a very specific physics question, and Stephen Hawking spent a lot of his time trying to figure that out. But what does that have to do with us on Earth? We don't really care about other planets. We can't get to them. We can never get to them. They're way too far away. Maybe Mars isn't. We're working on that. But we have to figure out how solar systems formed first. And that is called the nebular hypothesis. Now, I need you to remember the difference between the nebular hypothesis and the Big Bang Theory. A lot of you might get that confused if you don't study your notes, but I need you to keep it separate, please. The nebular hypothesis is the idea of how solar systems form, not the universe. That's the Big Bang Theory. We take a whole bunch of dust and other kinds of stuff that's floating through space, and eventually it compacts in due to gravity. And we have these clouds that start forming because gravity is pulling it closer together. And then eventually it gets to our solar system, and we have the 8, formerly 9, planets that are listed on your notes. Now, I didn't mention this before, but what I'm talking about right now is your notes. It's going to go with the slides. It's going to go with the paper notes. We're going to talk about it in class. I'm just doing this because obviously we can't all be together. This is meant to help you out if we're not in class together. Now, some of you are going to have notes that go along with this in class, and some are going to do them outside of class, but we're all going to have to move together. So we get to the shape of the Earth. Now, a lot of you might think it's a sphere, and that's pretty close, but technically it's not a sphere. It's what we call an oblate spheroid. And an oblate spheroid means it's wider around the middle than it is around the tall parts. So our Earth is a little bit fatter around the equator area than it is around the prime meridian area. Remember, equator is flat, prime meridian goes north and south. This is due to how the gravitational area and all that stuff, the physics basically spin the planet. Think like a pizza. You take a ball of dough and you spin it on your finger. If you can do that, it's going to flatten out. That's kind of what the Earth is doing, but don't worry, Earth's never going to flatten out like that. We're in the Milky Way. Now, I think a lot of you probably knew that as you came in to this course. You didn't mean to tell you that we're in the Milky Way. But you probably didn't know that there's about 100 billion, again with a B, observable galaxies that we can see. Observable means we have a way to see it. Now, maybe our eyes can't see it, but we've built technology and telescopes and infrared and radar and all, not radar, I don't know why I said radar, and all this stuff that can look out into space. In just ours, in just the Milky Way alone, we have over 100 billion, maybe up to 400 billion stars. And that's important, but we care about one star in particular. You already know which one that is. It's responsible for our day and night. And how does day and night happen? Well, it happens when an orbital body, Earth in our case, spins on its axis, and we call that rotation. Rotation is when an orbital body, a planet, spins on its axis. Revolution is something that's a little bit different. Revolution is that orbital body, Earth, going around a fixed point in space. Now, what point is that? It's the sun. And we're getting ready to go into seasons, and there is something incredibly important I need you to remember about seasons. As we go around the sun, obviously that makes a year, but our seasons are heavily dependent on this factor and not the one you probably come up with in your head. It is heavily dependent on the tilt of the Earth, which is on average 23.5 degrees. Now, this is important. It is the reason we have seasons. It is not, I'm going to say this a million times in this unit, it is not our location to the sun. How close or how far away we are from the sun has nothing to do with our seasons. It all has to do with the tilt of the Earth. Now, I'm going to show you a couple maps, and you're going to see, or not maps, but graphics, and you're going to see that in the winter and in the summer, we're not where we think we might be if we just went purely on distance to the sun. We have a couple different days. There's sidereal and solar days. You don't really need to know the difference, but what you need to know is that we do have to use these differently when we're talking about whether it's physicists and astronomers and stuff talking about a day, or whether it's you and me talking about a day. A sidereal day is just how long it takes Earth to spin and get to the same background, basically, in space. A solar day is what we use. It's 24 hours. It's how long it takes to the sun to go from top dead center, as we might say in car speak, 12 o'clock noon to 12 o'clock noon the next day. So, sidereal, solar, just remember that they're a little bit different and we use solar days. Now, back to the aphelion and perihelion. Again, this goes back to our seasons. Now, we just said that it's due to the tilt. It's not due to how close we are. You'll notice that the aphelion, the point that we are the farthest away from the sun, is actually in July. It's in the middle of our summer. And that our perihelion, the point where we're closest to the sun, is in January, our winter. So it is not how close or how far away we are from the sun. I'm going to ask you that on a test. I promise I'm going to ask you that on a test. It has nothing to do with that. It all has to do with the tilt of the Earth, the 23.5 degree tilt of our axis. So why do I keep harping on this? Well, because you really need to know it. And what you might get confused, and you might have all these preconceived notions as we move forward, just remember that this is going to be a shorter video. I'm not going to have you do a whole lot, and if we get off a little bit in class, that's okay. Our pacing may not be great here at the beginning, but just remember that these videos are here for you to study, and if you're off on that day, if you're not in class with me, I need you to be doing these as we go along so we can all get to the end of the unit together. I'm also going to leave them up for the entire semester, and you can use them as review, and wherever my notes end, so in this case the slide that we just ended on is where the next one will start. So they're here for you. Let me know some feedback on them. Let me know how they can help you more. It may not be your favorite thing, but we got to do it. We have to do what we have to do if we want to be able to see each other at least a little bit in class. And if I can do anything to make these better or to make these a little bit more memorable, then let me know. I'm making them for you. They're not for me. They're for you. They're to help you study. They're to help you do well. They're to help you make hopefully an A on the test. And I will see you in class soon. See you for this one. Bye.